Hello everyone, this is DA from E Academy. Today we will talk about direct method that leads toward the finite element method. So let's get started. Let's draw a simple bar in one dimension, started from 0, having length L. This is the actual continuum. This is the bar. Why I'm using the word continuum here? Because this can be represented as the assembly of interconnected elements, finite elements. And there is the continuity in every element. If I'm moving from this element to this element, then there is no discontinuity. Where we need to know what is a node. So the point on the boundary of the element is a node. So we have divided this whole element into sub-elements, and now we not have only one element. We have 1, 2, 3, and 4 elements. And how many nodes are there? We have node 1, node 2, node 3, node 4, and node 5. So what is a node? We can precisely define the node as points that usually lie on the boundary of an element, where adjacent elements are considered to be connected. So we usually represent the node, the number of nodes in an element, n, small n. Now the point is, if we're talking about the whole structure, how many nodes are there? 1, 2, 3, 4, 5. So we have 5 nodes in total in the whole of the structure. But when we're talking about in individual elements, then we have 2 nodes in each element. So here we have 1 element, there we have 2nd, here we have 3rd and 4th. So every element have 2 nodes only. So this is for the whole geometry or whole structure, and this is for the element level node numbering. So how we distinguish the whole geometry node numbering with the element level? One, we will represent it. We will add E on the subscript of it. So when there is a subscript, we will say that this is the element level node number. So generally we don't say the whole structure, we say we have a global numbering and we have a local numbering, or we can also say that we have a global coordinate system or we have a local coordinate system, in which we have to consider the whole structure. In this, we only need to talk about one element at once. And here we have to specify the number of elements as well. So as we have seen that nodes, the number of node is represented with small n, and the number of element is represented by the capital N. So how many elements do we have? 1, 2, 3, and 4. So capital N is equal to 4, and there is a connection between node and the number of element. Number of nodes is equal to number of elements plus 1. So this is the relation between small n and capital N, but this is only for the linear elements. This is not for any quadratic or cubic or whatever we are in the higher orders, but this is only for the linear elements. And linear elements are the basic elements, and we will most of the time dealing with only linear elements, and that is why this is very important here. That is for the linear one-dimensional elements. We have a relation between number of nodes and number of elements. So what we have done so far, we have divided this whole domain into 4 individual elements, and this is what the first step of the direct method is. The first step is known as, we should write it in red so as to make the correspondence. So direct method, the first step is known as discretization. So the first step of this direct method is discretization of the whole domain or the whole structure. That is what is basically in the discretization step. We need to specify the number, type, size, and arrangement of the elements. In the next step, that is the approximation of the function. Approximation function is also known as interpolation function, and these functions are actually defined in the terms of the primary variable. Why I'm saying the word primary variable here? Because we haven't defined the variable so far. For example, we have to figure out the displacement. For example, let's represent the displacement with u, and that is depending on the values of x. So u is our primary, or we can also say that it is the field variable. So these are the two terms that we will use when we say we have interpolation function or approximation function. So u is, in this case, it may vary according to what you have in the structure, what you have to figure out in the complex geometry. So let's assume that u of x, that is our approximation function, is a linear function. Why? Because we are dealing with a linear one-dimensional problem. So the most simple polynomial when we have to say that we are supposing a new function, approximation function specifically. So let's suppose we are saying that a plus b times x. And what is a and b? A and b are constants. Now the question is why we assume it as our approximation function. The answer is that we can't just write the exact function that describes our structure. Here we have only a simple bar, but in the practical problems there are many complex geometries, so the main point is that we can't write the exact function, so we have to approximate it with a simple one. So we just look the simple function in the one dimension that is linear as well, so we came up with this approximation function. But there are also some restrictions when assuming a approximation function. The restriction is that apart of being simple, it must satisfy the convergence requirements. So what does mean by the convergence requirement? Because in each element we have two nodes, and when we say that we have to satisfy the convergence, so the convergence is associated with the point of the continuity. When we are seeing this bar, the value of element 1, the value of node 2 at element 1 should be equal to node 1 of element 2. And why this property is important? Because in each level we will be talking in the local coordinate system. Combining both of the coordinate system, the continuity is the key to bind them together. So that is why this property is very important. And the local coordinate system and the global coordinate system plays a very vital role, because our 2 to 3 steps are just in the local coordinate system, and then we have to assemble all of the things together in order to get the whole idea and then figure out what is the required thing that we will need to find. Let's derive the approximation function for this bar. For example, at x is equal to 0, if we put this here at 0, we will a, and we will suppose that at 0 displacement is u1 having any value, so a is u1, and at the other end x is equal to l, So u of L is equal to A plus B of L. Here suppose that the value of u at L is u2. So you can name them according to u, and A is u1 plus B times L. In order to figure out the value of B, let's eliminate things. We will be B is equal to u2 minus u1 divided by L. So here we have the value of B, and here we have the value of A. So when we plug the values of A and B in this, we will come up with the function that u of x is equal to u1 plus u2 minus u1 by L times x. So this is the required approximation function for our bar, and also use it on the element level by just using the subscript e on it, and L is also e because the length, this is the total length, and if we have to discretize it into many elements, then L is also divided. And here there is an important point that this the length of each element needs not to be same. It can be different. For e is equal to 1, it could be, for example, the length of E1 is 2 meters, and for E1 is 2 meters, and E2 is, it could be 5 meters, and so on. So this can be the case, but it can be same. So we have derived an equation for our problem, that is the finite element equation, and that is very important because we will need it in order to find the specific displacement values at specific point. So far we have discussed two steps of the direct method. First one is discretization of the structure, and the second one is approximation function, and we have the finite element equation from this. So we will continue this in the next video from the third step. So this is for now. Looking for more such videos, then you can subscribe this channel in order to watch more upcoming videos. We will meet in the next video. Till then, take care. Goodbye.